So today we are going to learn from him the statistical properties of Chatterjee's direct correlation.
Thanks a lot for Chuan to introduce me. So today I will talk about Chatterjee's correlation coefficient. The problem is very simple. All right, it doesn't work. The problem is very simple. It's just about measuring the dependence and testing the independence between two random vectors. One is p-dimensional, I denoted x. Another is q-dimensional, I denoted y. I would be interested in knowing how correlated, dependent these two random vectors are. And also testing whether they are independent of not or not. And of course, we are statisticians, so may make our decisions based on data. So data I have is just the simplest one. I have ID observations of x and y. So I'm going to answer my question based on such a simple ID data of sample size. So this is the question, the setup. All right. So now, because this question has been super fundamental, elementary, I would like to set up some criteria for answering my question. So the criteria I will choose is based on Alfred Ring, who is like a legendary information theorist. So surprisingly, he also did something about dependence measures. So this is based on his 1951 paper. We propose the following three rules for any dependence measures. The first rule is this dependence measure should be between 0 and 1. 0, 1, these are two numbers, probably natural to human beings, and I'm going to use it. The second one that is very interesting is this dependence measure should be 0 if and only if x and y are independent. All right, excluding many very well-known correlation coefficients. The third one is, in my opinion, even more interesting, is this measure should be 1 if and only if x and y are perfectly dependent. That means the sigma algebras are same, or in other words, y is a natural function of x. All right, perfectly dependent, functional, deterministically functional correlated. So these are Variance rule. So Ray is a mathematician. He doesn't care too much about estimation. So we are statisticians again. So for data analysis purpose, I would like to add some additional criteria. The first one is I hope the estimator, if there exists, for estimating this dependence measure, it should be computationally fast. We are in the age of big data, deep learning these things. So for implementing such an elementary program of measuring the dependence, I hope it to be computationally. And ideally, really linear dependent on the sample size, the computational task. The second one is our statisticians' existence is this estimator should be efficient in the statistical sense. That means for testing independence and for estimating the dependence, it should be efficient. All right, now here's a roadmap. This is a super classic problems. And the first question is what is new? And for answering that question, we have to go back to the history. Let's see what the great statisticians studied and how they got so far. All right. So the greatest statisticians living in 1960s, 1950s, they studied simpler Bivariate data, not random vectors, but random scalars, x and y are one-dimensional. And I had one assumption, that is I have continuous marginal CDFs for simplicity. And then it is very well known, the satisfying Ray's second criteria, we shouldn't use Pearson's correlation. It is that Y1 result tells us 0 Pearson correlation doesn't mean independence. And something I really like, the Tenders-Tau and the Spearman's row rank correlations. They are based on ranks, so they are super robust. They have a lot of appealing properties. They are invented by the greatest British statisticians of that time. But again, it doesn't. The population of Tenders-Spearman's rank correlations, it is 0. It could be 0 for some dependent random vectors, random variables. So again, we cannot use Tenders-Tau Spearman's row. But just satisfying Green's second criteria. So what should we do? For getting independence if and only if 0. It turns out we have a legendary statistician jumping out to answer this question, Vasily Hopdin. So Hopdin's insight is done with a measure of dependence, a populational measure of dependence. It defines this one, which we now call the Hopdin's D. It is just measuring the mean squared difference between the Bivariate CDF and the marginal CDF's productions. It makes sense because we know independence happens if and only if F is equal to F1 times F2. And it is not surprising Hopdin got this result 5 years ago. EXY between 0 and 1, check. If F is absolutely continuous, not a super strong condition, then if and only if. Wait, right? And then how to estimate it. As a statistician, of course, I need to consider how to estimate his populational dependence measure. The trick leading to U statistic, that is Hopdin's, like one of his trademarks to represent his research. The idea is super simple. You got this mean squared difference. You expand it because integration is a linear operator. I can do this one. And then here's one trick. Everybody should be able to prove it is equivalent. This integration is equivalent to the summation of these 3 terms. And here x1, y1, and x4, y4, x5, y5, 5 are the observations of xy. You can prove it, trust me. And then, now you have the population expectation version. You only have to, for estimating it, you only have to change population expectation by the sample expectation, that is the sample mean. And here it will lead to, because we are taking expectation over at most 5 terms, 5 tuples of xy, now then you get a U statistic involving like a 5 index summation. All right. And Hopdin is able to show a lot of very interesting results about this statistic. And one of the most interesting one he discovered in his 1948 paper is this one. It is under independence assumption, we have such a convergence of distribution for Hopdin's statistic. It is weakly converging to a non-Gaussian distribution. In retrospect, it is actually the first result about degenerate U statistic. And the fact is that it's converging in distribution to something non-Gaussian actually characterizes the degenerate U statistic. Well, it's super well known now, but thinking about it is developed for 75 years ago. Really amazing. And then based on this result for testing independence, we can then set up a one-sided and directly implementable test because we now know the limiting non-distribution. Why one-sided? Because the population motion has to be larger than 0. All right. So now let's check about Hopdin's D. Whether Hopdin's D has answered our question even before running it. So it is a dependence measure between 0 and 1, yes. It is 0 if and only if independence, yes. It is computationally fast and didn't mention, but it is. It is done by Hopdin himself. As if this is a new statistic involving some of the 4 tuples, actually Hopkins himself developed an algorithm to calculate it in nearly linear time. How smart it is, right? And lastly, it is statistically efficient. You can buy me. So it is statistically efficient. In the QMD alternatives, that is local asymptotic normality assumptions, under these assumptions, it is return consistent. So its treatment efficiency is larger than 0. Rate efficiency at least. And then let's think about the last one. Actually, when we think about the last one, the question I pop out is, Hopkins is actually a very good measure of independence, but maybe not a really good measure of dependence. You think of his formulation, its message of how dependence one X is actually weak. And at least it doesn't satisfy it is one if and only if it is perfectly dependent. No. It doesn't measure that. All right. Motivating new research. This is the first part result. Actually, some of them are really new, and I got one honors and one metric about it. I hope these journals manifest that indeed new, maybe. So solution, the second solution, again by good mathematician, statistician, researcher at least. Rain himself, Alfred Rain. Rain knew Hopkins' paper, but I believe he didn't think it is a good measure of dependence. So he proposed his ones. It is not called the Rain's correlation or the maximal correlation. It is commonly used at least in time series for depending rate mixing, if you know. So the measure, this is a populational measure, and the rate here is the populational Pearson correlation defined over all the L2P functions. I can define, and then I take the maximum of them. It gives a maximal correlation, of course. And here is able to show his dependence measure satisfies the first between 0 and 1, of course. Second, 0 if and only if independent. Yes. Lastly, a little bit tricky one. It is 1 if, but not only if. X and Y are perfectly dependent. Actually, the Rain's 1959 paper will find a very intriguing remark Rain made about this part. It's sort of like saying, okay, I give up here. There exists one, so that it can be if and only if. It is 60 years ago. We can agree that he has done enough. And in addition, how to estimate maximal correlation. Tons of papers, many of them published in Annals of Statistics. But my message from these papers is, it is still challenging. Lots of trainer trait, a lot of analysis, a lot of Gaussian theory, empirical process theory. Okay, I know them, but it is still challenging. All right. Even now, there are still new research. Actually, this week there's one archive paper still talking about how to estimate maximal correlation and how to fix the problem. Right. Now let's come back to Rain's criterion for his own proposal. For the first three, yes, nearly. Computation fast and no way. Efficiency, no way. We don't even know how to get the limiting distribution. How can they even say about its efficiency? So it goes down here for about 60 years. It's kind of one of the general independence measure says this is like the grail independence measure problems. The holy grail. And we need the greatest max, our Lancelot, to counter it, to retrieve it. And it is, of course, the greatest of our own. Structure. So the structure approach, which I will outline very soon, started the problem when we have a two-dimensional X or only one-dimensional Y. All right? This is the setup. And for simplicity of presentation, I only consider continuous data. Structure didn't, but for presentation simplicity, please allow me to only present his results of continuous data. Then here is one result got by Betty, Siebold, and Stoyanov in 2013. They define a very interesting dependence measure. They call it Kasai. All right. So this one is brilliant, but it was unfortunately not published in a very visible journal. It was only published in Scandinavian Journal of Statistics, which is a very good one, but not many people notice that. But this is actually a brilliant population dependence measure. Also, it is belong to 0 and 1. You can prove it. It's just by the law of total variance. You start maybe 2-1, maybe 4-1, I don't know. Then you can prove it. And actually, it's also not hard to prove if y is independent of x, then precise 0. Similarly, not hard to prove if y is a natural function of x, then precise 1. To give you a reason, you can read it. And what is interesting is the converse also holds. So these if, they're actually if and only if. So this is actually the first time we got something about answering Variance question. But Betty and Siebold and Stoyanov gave us again a kernel estimator involving 2 bandwidths, and we later found there's some problem about the proof of the limiting distribution. So that paper is kind of like not that great in terms of really answering our question. But 0 dependence measure is touching the grail, the holy grail. And then how to estimate. The idea is simple, actually. Let me introduce 2 notation. I is the rank of y, among 1 and 2 and 1. So we're ranking the data. The smallest one has rank 1, the largest one has rank n. I is the rank of y. So if y is the smallest, it is R1, I is 1. If the largest, I is n. Correct? AI, the indexing the nearest neighbor of x. So if x2 is the nearest neighbor of x1, then n1 is 2. Correct? Then here is the celebrated Azadic strategies, correlation coefficients. I love this stuff here, so you can truly appreciate how beautiful it is. I got the feeling that I'm not living in the age of Caesar and Augustus, where it is very peaceful but intellectually boring. That's we got something that matches the greatest time of Plato and Aristotle. That type of evidence should live in the age of Vasily Hopkin, but not in our useful but boring time. Anyway, what they can show is this is a strongly consistent estimate of person. This is strong. I have known him since the beginning of my study as a PhD student, but this one really got me. Okay. Now, let's chat about stress. It is between 0 and 1. It is if and only if. If and only if. It is computationally super fast. We just have to read it. Ranking problem is nearly linear. Summation is linear. It has to be nearly linear. A nearest neighbor group can be done nearly linear, so everything is nice and fit. Efficiency. So now we have a problem. And now is the time I can contribute. So far, everything is not mine. Non-distribution. What is the distribution of his cosine, 1, x, and y independence? 1 and the 3, wrote it down as a conjecture. I don't know. We don't know whether it is asymptotically normal. We don't know whether it is a root term consistent estimator. We don't know. So that's my research. So my contributions are fourfold, consisting 4 results, 1 with 1 paper. Let's go from the first one. the limiting non-distribution. As I emphasized, it is acknowledged as an open question in 1 and 3 of the Arnold's paper. And here is my answer. Our answer with my long-term collaborator Matthias Dutton, who left me to Germany, to his hometown, and my student Hongjian. The assumptions, very macro assumptions. I need y to be continuous and independent of x. I need x to be absolutely continuous. Maybe not too strong. Well, as long as they are holds, they have this rate convergence. It's converging to this normal distribution. Here, QP is a regularized incomplete beta function, and OP is essentially is mapping the volume of the overlap of two bits. And the key message is both parameters are distribution free. So Suarez, Azaki and Suarez correlation coefficient is actually a distribution free statistic, at least asymptotically. Why distribution free? Why distribution free? I will give you the intuition. So to prove these results, the first step is we are going back to the OD and Judy's. This is a reformulation of Tresine. I show there are asymptotically equivalent. It shows under independence, and its asymptotic equivalence is in R2P sense. And if you know one of Mark's asymptotic statistics book, this is Hájek representation to credit it to Yaroslav Hájek, statistician and mathematician. And here I didn't see what is H, but H is just a deterministic function. I will give you the closed form later. And Fy is the marginal zodiac of Y. And they are asymptotically equivalent up to a small √10 tau. And with these results, now let's see what is it. It is not only about summation and about the nearest neighbor graph of x1 to xn. x1 to xn are RID observations of x, and it's very well known in random geometry that nearest neighbor graphs has the universality property. And the two universality property I need is just these two, and then we will see what is the QP and OP. So universality means which we prove, actually, one of them is this one. Is if you have a random neighbor graph, average number of the nodes RMG, that is the nearest neighbor of each other, they are tuples, they only connected to each other, is converging to QD for a two-dimensional data. The second one is the average number of the triple, where R and G has the same nearest neighbor, that is K. So the two nodes share the same nearest neighbor, is converging to OD. These are the two I needed. And it holds as long as the random vector we observe are absolutely continuous. And this is why I need absolute continuity with respect to the beta measure. With these two, I'm done. It may seem like a bit scary, but actually, while it increments the calculation, it's some naturally pop out. All right. I'm done with limiting distribution. I'm happy I shared it with a lot of my peers. They are happy as well, but then it doesn't finish the problems. Our quest is what would be the limiting distribution if x and y are not independent. Because this time we are actually studying a dependence measure, it is not only about testing dependence, it is also about inferring the dependence measure. So it's very natural we need to get the limiting alternative distribution. Again, open. Here's my results, and probably my most powerful results. I will give you a reason. So I show, as long as y is not a natural function of x, which is the degenerate case, And Schwab said when y is a measurable function of x, then actually cosine is a deterministic constant. So I don't need to say anything. So I assume it is not a measurable function of x. And it's continuous. I drop the absolute continuity assumption. Only continuous. Then the normalized version is converging to the standard normal. Why I'm so proud? Because when I share this result with Schwab, I got his permission to brag it out. Schwab says, if I have the pleasure to read, I try to prove these central theorems in my paper, but couldn't figure out how. So I'm very impressed. I will let you know if I have any important remarks. I didn't have any. All right. I'm so proud. You know, that's Schwab. Why? How? Why is so challenging? Review on a limiting line distribution proof. We prove this Hájek representation under a very important independence assumption. Why I need independence? Because of the independence, the ranks of y are independent of the nearest neighbor graph of x. So I can do a conditioning trick and fix x1 to xn. It doesn't involve the distribution of R1 until Rn. And the ranks, when them are, right? Mathematician combinatorics is related. Ranks are just combination. It's a uniform combination. We have ideal observations. Uniform combinations combinatorial central theorem. And Marcelo Harding proved combinatorial central theorem about 8 years ago. So I got everything done. It's a pretty classic mathematics proof. But if now I deleted this independence assumption, now I'm going to, if I do conditioning on x1 to xn, I have to deal with a permutation that is not uniform. Because how large xr will change the distribution of R1, Rn. I need to try such a dependence. And actually, I know several proofs, many brilliant statisticians, RSI graduates, also in math, they actually told me it is impossible to establish such results if they don't have independence. But we managed to get it. But this is actually the limit of our central limit theorem proof. As we show that as long as x and y are continuous, this approximation always true. Even though y is a measurable function of x, it is still true. How many minutes do I have? Great. Oh, I get it. I won't give you a lot of details, but I wish to give you the most important trick. The trick is, again, OD and building Hájek projection. So let's say the main term in cosine, so say this term, I deleted one, it doesn't matter, right? And Hájek has this brilliant trick about how to study a general statistic that can be heavily correlated. We call that this is not an RID summation. No, this is not an RID summation. They have really, very strange correlations between each other. It will change in the summation. Hájek has this idea that in general it should be true. It should be similar to this one. And what is the good thing about the right-hand side is when you take the conditional expectation, now it becomes ID. Because the conditional xk and yk, this is only a function of xk and yk, which are ID. Of course, establishing such Hájek projection results is super non-trivial. Super non-trivial. We got like 30 pages of calculation. And once it is done, you sort of get the idea how to proceed. If you check this one, you can rewrite it as a summation. You can separate the summation to two parts. One part is about yk, that is the conditioning k. The other part has nothing to do with k. the conditioning part. And then I can, according to this decomposition, separate the summation to two parts. The first part involves nothing about K in the conditional expectation, nearly nothing about. The other part is all about K. And for the first part, is now how to show this is the first term in the Hájek representation formulation. For the second part, a drawn-sum calculation gives us this is our HYK. And this is an H function. That is, of course, a deterministic function. Only depending on the joint CDF of X and Y. All right. Don't need to follow them. I just wish to give you the most important message is Hájek projection. If we try to reason like the random forest analysis, Stephen Weidler's proof of central limit theorem for random forest, they also use this trick. It's very relevant even in the big data age. And in our case is a second proof. It is relevant. All right, once this data is done, it's almost done, but still non-trivial. We have a nice central limit theorem, but this is a graph-based central limit theorem problem. But we have a drawn graph. Help us settle this part. The swaps and also probability paper, 2007, right? Should be. It gives us a nearest neighbor central limit theorem. And using his tools, we are able to now show this Hájek representation of cosine has a central limit theorem. And because this is equivalent to cosine, asymptotically, then cosine also has a central limit theorem. Okay. You may ask about, okay, I know how to get the central limit theorem, but for inference, for constructing the confidence intervals, we need to estimate the variance. The short message is variance will also know it. We show the existing variance estimate so that this variance estimate is a consistent estimate of the asymptotic variance of cosine. And if you are interested in knowing its form, this is the form. Probably the form itself says it is non-trivial estimator. Yes, it is non-trivial. I share, for example, with Holder Daddy, like send me an email saying, how do you get it? I can only reply, maybe that's not. Anyway, so we get it. So this is the consistent estimator. Now, the next question, which we were asked by our peers is, I know these are mathematically interesting results. Our limiting distribution of data, that's good, congratulations, but in practice, we all just use Bootstrap. I'm not just using Bootstrap. Very good question. The only thing is Bootstrap doesn't work. So you still have to use our central limit theorem. So this is the result. We have central limit theorem. We're not simply using Bootstrap. Very well. Very good question. It is not consistent. How to formulate? We have if X and Y are random scalars, continuous and independent. I add scalars condition, but this is for proof purpose. It is still not working for the scalar for the vector case. But for proof purpose, we simplify it. And also for the simplified to be the independent case, simulation, you can check our paper. Simulations show it must not be bootstrap consistent in arbitrary case. It is always not bootstrap consistent. But we are again only able to show, to prove the bootstrap inconsistency and the independence. And then cosine at B is the bootstrap version. This is Afron's bootstrap. I'll need a lot of details here. You can imagine what is Afron's bootstrap do, right? So it's a sample with replacements, and then just calculate swap charges correlation on the sample data, and then that perceptual B. And then we can show that the bootstrap variance we have two versions. One is centralized by the estimator based on original data. The other version is just calculating the sample variance of the bootstrap over the bootstrap distribution. Both of them do not converge to sigma square that is the asymptotic variance. And in addition, because it's variance inconsistent, it should also be distributional inconsistent. Of course, we can use Pitman's theory since this one is not bounded, but we can use something, just a brutal calculation. We can also show that there exists a major non-zero subset of the whole probability space, so that around this set, these two distributions do not converge to the limiting non-distribution of percent. So distributionally also inconsistent. And now we try to do that a little bit more because we really like this result. Why do we like it? Think about it. We have shown percent is root-n consistent, is asymptotically normal. And surprisingly, this trap fails. This is a quite interesting case. We will also do a rising case. So now we go back again to OD and GD results. This come by Rudy Boran. You should know him if you didn't know. Berkeley statistician, doing a lot of bootstrap theory. So this is a very little known result published by him in 1997, not many years ago. It proves that, I need to emphasize it, it proves that in a local asymptotic normality model, a long model, bootstrap consistency is equivalent to regular. That estimator is a regular estimator, which means its distribution doesn't change in a rather root-n neighborhood of the parameter. It's equivalent. For example, super efficient estimators like Hájek's estimator, Stan's estimator is not regular. They are not regular. So this result implies Hájek's correlation has to be nowhere regular in any long model, such as the Gaussian rotation model, the Bivariate Gaussian distributions. Nowhere regular. Even though it is root-n consistent and asymptotically normal, it is irregular. So he gave like a textbook counterexample of some common understanding of bootstrap consistency. Okay, the last part, how many minutes do I have?
10 minutes. Yes.
Oh, still about 10 minutes. Great. I think I should be able to finish in maybe 5 minutes. All right, so far everything is nice and clear. We have the first three conditions hold for Schwab's correlation coefficient. It is computationally fast, of course. Efficiency. In terms of estimation, that's good. We have root-n consistent. Root-n is the parametric rate. We cannot be better than that. But how about testing independence? Unfortunately, Schwab's proposal is not efficient in testing independence. This was discovered by Peter Beetle, by our group, and also by some ISI brilliant students. So we are about to fund it at very close times. Actually, Peter and our group got the results in the same week. So this also means this is an important problem, right? Because people are rushing to study it. So let me give you the reason. The reason is very easy to understand. The reason is because if you check their formulation, it's based on the one nearest neighbor. If you learn like a non-parametric theory, like for example, if you are using the nearest neighbor to estimate the PDF, the probability density function, we know the one is not efficient. It's actually creating a huge variance. So one doesn't fully utilize the data information, and this is why it is not efficient in the very high level of the reason. And once we think about this, the fix is very easy. It's natural. We just have to incorporate more nearest neighbors into it. But the question is always about theory. We are not deep learning guys, we need theory. So for getting our theory, unfortunately, I need to add some assumptions. So the first one we get is I have to assume now this time again actually is one-dimensional. And second, I'm using the right nearest neighbor. Because it is one-dimensional, I can always pick the direction, right? It is either right or left. So I will only use the right nearest neighbors on the right-hand side. That is ones that are larger than the starting point. And then I need to index the arm's right nearest neighbor of x. And then this is my proposal to boost the efficiency of swap strategy and monadizability as correlation coefficient. You just roll the right sum. This is the only, nearly the only change. I also changed the denominator a little bit. I will talk about why later. So now this sum, I'm enrolling the top arm and the nearest neighbors of I to the formulation of my statistic. So that as an M here, which is a tuning parameter. So what do we care about this new proposal? When we have bivariate data, this is our results in parametrica. The first is as long as M is ignorable compared to N, it is strongly consistent. Second, as long as X is independent of Y, I'm using this notation to mean independence. And R goes to infinity, but not too fast. The change point is n to the power 1/4. It's actually a natural change points. Many non-parametric program has this change point. They have central limit theory. And even better, I can calculate the explicit form of the mean and variance of psi. It is mean zero. It is mean zero. That means that explains why I deliberately use this denominator. So this one under independence has mean 2. And it has this variance form. It is always true. And lastly, based on the above three results, I immediately plot this power analysis. The power analysis is psi is distribution free. We can use simulation-based test of independence, and it is arbitrarily close to the return consistency criterion, the parametric rates. If we pick the arm to be arbitrarily close enough to it. So think about different arm will give us different detection boundary. That is a local finite closer and closer to the fully independent case. How closer it can be so that we can still have the power give us the detection boundary. And we reach the detection boundary to be n to the power negative 1/2. That is the parametric detection boundary. And here is the graph. So X lab is how large M is. M is n to the power gamma. If gamma is 0, that is M is a deterministic constant, then the detection boundary is n to the power negative 1 total. This is the detection boundary the 3 ISI students got in the 2021 paper. When I increase M, I drop this detection boundary. So the solid line is the one I can show this is a critical detection boundary. And the dashed line means I can only show this is a sufficient detection boundary. Not, I do not have a low point to match it. This is why I did not submit it to Ines. It's only a biometric paper. I really like it. So you can see the sufficient detection boundary that will match 1/2 if arm is actually close to it. So choose gamma to be 0.999 if it's super close to 0.5. That is the parametric detection boundary. In addition, you see this like there is a change point, there is a change point. Actually, in this part, when you increase ion, actually the power is decreasing. The detection boundary is decreasing. This is because of the variance bias trade-off. And remember, this is not a minimized. It is not a minimized detection boundary. This is a detection boundary of a particular procedure, my proposal procedure. So such curve makes sense. All right, let's review. Then check out our criteria. The first three still hold. It is not efficient, I would like to say. Computationally, it got me. When I have a big ion, actually, it is not merely linear. It is as worse as erratic. When you have ion close to it. No free lunch, huh? So this is still like open question. Some people asked me about conventional to achieve all of them. Computation it is important to have merely linear, but I don't have the tools to do it. It's like a TCS problem, theoretical computer science problem, to show the mean low bound for computational efficiency. And usually such low bound can only be shown for NP and P problems, but not linear problem versus quadratic problem. So I don't know. It would be nice to see a theory. All right. To end with my talk, I give you some open questions to think about it. One thing I never really discuss a lot in order to not confuse everybody is debiasing. So the sampling theory here is expectation of percent, but not percent itself. It's not a population dependency measure. The reason is because only if I have a binomial data, I know this expectation is small rather return compared to this side. Once I have X to be larger than one-dimensional, this part is not asymptotically ignorable. So that means my confidence interval, they can only work when I have Bivariate data. So how to debias percent so that I can recover my confidence interval even for higher dimensional? That's so it's the open question. I believe we got some idea how to debias it. So if you're interested in these problems, I highly recommend Richard Summers, Ming and their students contacts. They have a 2019 paper. They started using Nearest model to estimate the entropy, the entropy. It is a highly related problem, and they got some fascinating results about debiasing. It's super technical, by the way. As generalization to higher dimension. So here, Y is only one-dimensional. Of course, we will ask how to generalize to higher dimension of Y. Many words, I can tell you many words are these problems, not all of them is appealing to me. I don't think we fully resolve this question as well as in one-dimensional. So I believe we still have some research to do. High dimension. Everything here, the probability measure, the fxy, the Bivariate CDF, or the generalized the CDF of x and y, we assume it to be fixed. It is not changing with the sample size. Dimension is not changing with the sample size. So if we are really going to study the high-dimensional version of Swap-Charity's proposal, I have no idea. I have to rely on my peers. Random matrix theory. Random matrix theory can be applied to study Chatterjee's correlation, because essentially you're giving me arbitrary pairwise correlation. I can get a random matrix, and then I can study its spectrum, all these properties. I know that in Hong Kong, they are studying these problems, but so far, based on my understanding, they haven't got anything. So we still probably have a chance. Everybody has the chance. And these are the 3 published works. Bernoulli biometric, 2 more animals and second round revision just released. So these are the works in our group did about it. And if you are interested in knowing more about this idea of strategies, I have a review. It's a very short 4 pages review. Should be reader friendly. You probably can take a look. And that's it. Thank you, everybody.
The last theorem. How big is the set on which y is not a measurable function of x?
Y is not a measurable function of x.
That's a sort of first assumption in your theorem.
Yes, I need y is not a measurable function of x. Yeah, you know that one. Yes, I knew that one. It's not.
It's an interesting assumption, but the question is how big is that kind of set where y or pair of random variables?
How to quantify how large this set is? Right? That's the question, right?
Yeah, another way I could ask, how can you test that assumption?
Yes, of course. This is actually Peter Beetle's interest question. He asked me this question. My answer is you can use my theory to test it. You just have to use my theory in a delicate way. That is, you are not, instead of testing whether psi is 1, you're testing whether psi is larger than points, for example. If you think psi is, if you're rejecting that null hypothesis, that means you are probably not having a fully measurable function. You can test whether psi is larger than any deterministic constant smaller than 1 using the central limit theory. This is like a classic t-test problem. For testing whether psi is exactly 1, it's my belief it is a ill-defined question. Because the reason is because Suar has said in his Jasa paper, if y is a measurable, is actually a strictly increasing function of x, then his correlation coefficient is a constant. It's super degenerate. It doesn't even have any randomness. Is that answering your question?
It did, thank you.
Great.
Right. I have a quick one. How this relates to secondly reason? Distance covariance.
Distance covariance.
They claim that they measure the dependence.
Distance covariance is just Hawking speed in a certain way. So it is a good measure of independence. It's not a good measure of dependence. It's my humble opinion. You check distance covariance, it's as some type of behavior is, it is also degenerate your statistic. It converts into the mixture of S class. It has all these nice properties of 0 if and only if independence. But at least it doesn't have the 1 if and only parts. And if you check its dependence, it's hard to interpret, unlike Hájek's dependence measure. It's my opinion, and I think some of my peers are doing this. Not all of them. Yes.
So do you have a variation norm for the asymptotic norm distribution? That is
a variance bound for the
variation bound, like how fast the non-distribution is converging.
very thin.
Right.
In short, I have it. Actually, I have trimal moderate deviation. I didn't do it anywhere. I review one people, they got something, they got it wrong, and then I tell them, you use this trick, you use this trick to get these results. Very simple, and at least in independence case, it's trivial. It's not publishable. But in the dependent case, it's not hugely trivial, but because it's about all the nice things about random correlations. Very simple, give you one more return. Trimal moderated deviation give you the critical boundary of the tail is n to the power of 1/4. Oh, sorry, n to the power of 1/3. To get all this, the best of all these random correlations. You can cover them for the swaps. So the biggest question for swap is this one, Bivariate. This is the biggest part.
How about using the permutation test, not bootstrap? Is it consistent?
Mutation is trivially consistent. Yeah. Of course, it is consistent. So I know many groups they do the permutational analysis. They go through it. So one thing I would say is, we got four different results. The limiting non-distribution, we've done a limiting non-distribution in order to show it has no power. Instead of actually using that for, well, in methodological level, you can just using permutation. It's computationally harder a little bit than just directly giving a critical threshold, but you can do it. But for analyzing the power, you have to get the limiting non-distribution. So this is the motivation of the fourth result. For the second and all the rest, no, you can use permutation to get a confidence interval, right? You decide.
Maybe you guys can talk to
Thank you for having me.